They never gave me any worry project yet, but I hope with the IPTV thing going on pretty well, they may be willing to consider that.
It takes a while before they sort of. It took me, last year was my first.
Oh, worry, really? So
right.
it took.
And I was working with them all these years.
Even as an insider, it just
right,
took a little bit longer.
So it takes a while. Like with the IPTV, we applied, it didn't work. With this other stuff, this Unicast CDNs,
I see.
Oliver and Colbus and that company, that worked out.
That's nice. So take some trials, I know. So.
Yeah, that's what I use to buy out a class this year.
Excellent,
because it's discretionary money.
Exactly.
It's disproportionately important.
Within itself, you cannot.
You cannot do that, right?
Yeah, so that's true.
Disproportionately important. Okay, so let's start. All right. So it is our pleasure to welcome Jun Xu from Georgia Tech. He is active in, I would say that his research straddles actually three areas. He is a theoretician by passion, I would say, but he applies his skills in the networking domain and in the database domain, I would say. He graduated, he's actually more or less local. He got his PhD from Ohio State. So when I was being apologetic yesterday during dinner about our weather, then I cut myself short because I realized, he knows. Okay, but I think that he's eager to go back to his warm Atlanta from our climate. Anyway, he got his PhD from Ohio State. He's an associate professor at Georgia Tech right now. He has his share of awards. He is a recipient of career grant. He is a double recipient of IBM Fellowship Award, Faculty Award, I'm sorry. He co-authored a paper with his student who got the Best Student Paper Award at Sigmetrics a few years ago. And it is my distinct pleasure to introduce him today.
Oh, thank you very much, Michael. So the title of the talk is Network Data Streaming. I call it a Computer Scientist Journey Signal Processing. And the reason why I call it this way is before during my graduate school years, I took one course in electrical engineering. I didn't quite like it. I think it's I forgot actually. It's a double E version of signal detection. It's a sequence. I think it's a 3-course sequence. I think it's like signal detection number 1. And I'm dealing with Gaussian distribution, all these things. I survived. I got the A, but I didn't quite like it, so I didn't take any other double E course. But once I become a faculty, I realized signal processing become more and more important in my research. So actually, but I never had any training. But by working on such topics, I feel I have learned a lot on signal processing. So that's the reason I call it a computer science journey signal processing. And I feel that as a computer scientist, I brought in some unique perspective, probably, which is not thought about by signal processing people by training. So I'm with the Network and Telecom group at Georgia Tech. And this is, I think, the work I'm going to talk about is joint work with my former students, colleagues at IBM and AT&T. So I first want to give some motivation to the work. So we often, in a high-speed network, we often need to monitor network links for a bunch of quantities. And actually, if you are not familiar with networking, you do not need to panic, because I think within the department, they often say that I'm not working on networking, because if you take away these terms, if you just look at the problem I'm working on, it can be applied to any domain. So so I think if I talk about like IP address or flow ID, it's just jargons. If you just think about it as like a data label, if you just think about data label, then it becomes a database problem. So we often need to monitor network links for quantities such as elephant flow. Elephant flow just means this particular flow has sent a lot of traffic. For example, if you all together within like 1 second, you have like 1 million packets. If there's one flow which sends like 100,000 packets, then it's elephant flow. It just means that. And sometimes we want to know other quantities like a number of distinct flows. So how many flows are competing for your bandwidth, for example? So this is number of distinct flows. Sometimes we want to know the average flow size. And you can tell these two quantities are related, right? Because if you multiply them together, that's the total number of packets you have in 1 second, which you can measure very easily using one counter, using just one counter. And then more advanced quantities you want to know include something like a flow size distribution. Flow size distribution just means how many flows have size 1, how many flows have size 2. Have size 1 means you have 1 packet in it inside this flow. Size 2 means you have 2 packets in it. It just means that. And sometimes you want to know the per flow traffic volume. Sometimes you want to just know the summary statistics of the traffic. For example, you want to know the entropy of a flow. And all these quantities can be very important, for example, for anomaly detection, for traffic engineering, for billing, for queue management. And there are other unlikely applications. For example, you can use data streaming to estimate the traffic matrix. So what is traffic matrix? You have like, say 100 access points inside AT&T, suppose. And then from every access point to every other access point, you could have some traffic flow. So traffic matrix just means if you look at this 100 by 100 matrix, what is quantity? So which means the amount of traffic which goes from any access point I to any other access point j. This is a quantity in the matrix. So traffic matrix is just this 100 by 100 matrix. And then you can also use data streaming. You can do other things like peer-to-peer routing and IP traceback, which I won't be able to talk about in this talk. So I want to quickly actually tell you a little bit about my personal history of getting involved in data streaming. Actually, I did not know anything about data streaming until I visited AT&T back in October 2002. I gave a talk there on totally unrelated stuff. I gave a talk on quality service. I did some kind of hardcore quality service work, which is like scheduling packets, delay bounds. And then I talked with some people, I think Misha might know, I think Anna Gilbert and Martin Strauss, and tell me something about data streaming. And to me, it's like a term from Mars. And then when I came back, I worked on some security project. And then because of the need in the security project, I have to come up with a data structure which allow me which is an extension of the Bloom filter. I think that Bloom filter is a pretty well-known data structure. And so I did this data structure, and then, but because this data structure is used for like a security, so it has to be like adversarial proof. And so in the course of minimax, because to make something adversarial proof, you have to do something which we call minimax analysis. So you do the min-max. And then after minimax analysis, basically I found out this data structure is not good for security applications. But then I think, I spent so much time on this data structure, so it has to be good for something. So if it's not good for security applications, it has to be good for something else. And then I tried to find the application for the data structure I came up with, and I realized it's quite useful, for example, for something like quite useful for this per flow traffic volume measurement. So it's actually my first data streaming paper called the Space Code Bloom filter. I gave it a good name because there's in electrical engineering have something they call I think space-time coding. So I think it turns out that I think space code fits very well into that particular work. So and I think this name is very easy to remember because of this space-time coding thing. Anyway, so I got into this field accidentally, and then suddenly I feel that I don't want to do anything else. I think there's a lot of problems in this domain, so I think I work on this like a set of data streaming problem for the past 5 or 6 years, and I very much enjoy it. So I think the lesson I learned is sometimes you just follow your passion. You work on something, and then it may lead you to something else, I think accidentally, and if you really like this something else, then you should follow your passion and you work on it. So that's the lesson I learned. But anyway, so the challenge of monitoring high-speed network is the following. because the network is very high speed. For example, in a 40 gigabits per second link, a packet will arrive every 25 nanoseconds. And then to monitor such a high-speed network accurately, you have to use SRAM. I mean, SRAM is like a very expensive RAM, and it's very small. So because it's very small, but the flow state is very large, so you just cannot fit all the flow state into SRAM. So the traditional solution is to use sampling. The idea of sampling is you can only use slow memory, so there's no way you can look at each and every packet, but you can look at each every 100 packets. One packet out of every 100 packets, you can do that. So it basically means you sample small percent of packets, and you process these packets using per flow state stored in slow memory. Because even if you're doing sampling, your per flow state is still going to be very large. And then, of course, the statistics you get from the sampled data is not the original statistics. So you have to use some kind of scaling to recover the original statistics. And the difficulty of the sophistication of the scaling depends on what type of statistics you're looking at. For example, if you want to know the total volume of traffic, even if you sample by 1 out of 100, you can still get the total volume of traffic pretty accurately, right? By multiply whatever you get by 100. But think about if you want to know the number of active flows, you want to know the number of concurrent flows, then you cannot do the simple scaling, right? Because if you have lots of flows of size 1, then if your sample rate is like 1%, then you really should multiply 100. But if but if you have some kind of traffic mix, if you just multiply the number of active flows you see by 100, it's not going to work. So actually, by doing sampling and scaling, we're actually fighting a losing cause. Why? Because the link speed gets higher and higher, so you have to use lower and lower sampling rate, and then you have to have larger and larger scaling factor, and then because whenever you scale, your error also scale up. So I think your error gets larger and larger. So network data streaming is offered as a smarter solution. So the computational model of data streaming is to process a large stream of data in one pass using a small memory, but it's very fast. For example, your SRAM is only like 1 meg or 2 meg, but you just use this 1 meg or 2 meg to remember very important information about the data stream. So the problem to solve is you need to answer some kind of queries about the stream at the end or continuously. And then the trick is to remember the most important information about the stream pertinent to the queries in this small memory. And those of you who know something about computer architecture knows that in architecture you have something called a cache replacement policy. So when knowing what to keep in cache is equivalent to knowing what to evict from cache. So it's the same thing. So basically, you have to learn to forget unimportant things. How to remember important things is equivalent to how to forget the important things. So comparison with sampling, I think I taught this data streaming course twice, and I always tell my students about the story. So when I was in the college, I don't like our curriculum very much. I mean, it's computer science, and I think they force us to. They think computer science students has to learn a lot of programming language. It's just crazy. I've learned like a Lisp, Scheme, COBOL, and all this crazy language, and so I don't like this kind of curriculum. So I usually do not study until like 3 days before all the exam dates, and then my task is basically a data streaming task. I have all these thick books. I only have time to do one pass, but I have to pass exams. So basically, the algorithm I use is to process a long stream of data in the book, and then try to glean the most important information pertinent to the exam. So I have some idea what the exam is about based on looking at the past exams and things like that. So I apply this data streaming algorithm, just remember the most important things in my I mean, pretty small memory, I guess. I mean, given that only a couple of days. So, and then, but it works. So I think I passed all the exams, and I arrived this far. So, but suppose I'm doing sampling algorithm, then I'll be in trouble, because sampling, if you think about sampling, it means I read page 1 of the book very carefully. I read page maybe 101 very carefully. I read page 201 very carefully, and absorb all the information. Then I'm not going to pass exam, right? So you have to do it very fast, and but you have to skim the book for most important information. That's data streaming. So these are the intuition of data. So sampling basically digests a small percentage of data and absorbs all the information inside it, but it's not going to be very effective. So streaming is very effective because you typically know the goal, so you try to skim the data for the most important information. So I want to give you a hello world data streaming, show you a hello world data streaming problem. The hello world problem is given a long stream of data, you want to count a number of distinct elements in it. So it's a classical problem. It's called F0, the zeroth moment. And suppose the data stream is like A, B, C, A, C, B, D, A, then this number is 4. You know, there are 4 distinct elements, A, B, C, D in it. But if I'm throwing trillions of objects onto the board and the millions of them different, then if I ask you to count, then it's very hard for you to tell me exact answer. So a simple algorithm, of course people will say, let's use hash table. But hash table is linear algorithm, right? The amount of memory you need to count using hash table is sort of the same, is linear with the number of distinct objects. And you want to do much better. So a simple algorithm is you choose a uniform hash function with range 0 to 1, which means you given any object ID, you hash it, you get the uniform random variable between 0 and 1. And then let D1, D2 be the data stream. The first piece of data is D1, the second piece of data D2, and so on and so forth. Then you just use one register. You use one register to remember the minimum hash value you have seen so far. Because of course, the same object label maps to the same number, or this random variable. So you just have one register which gets the minimum number. You can do it, right? Basically, you set to be plus infinity. With the number, the object comes in, you hash it, you get a number, you compare with the current number. If it's smaller, you reset to the smaller number. And then this thing is actually a random variable because of the hash function. The hash function is a random function, so this is a random variable. But you can prove that this random variable, the expectation of this random variable is 1 over F0 plus 1. F0 is the number of distinct elements in it. Why? Because think about that. If you have 6 distinct elements in the stream, then they result in 6 points. 6 uniformly random points within 0 and 1, right? And you cut this range 0 and 1 into 7 pieces, right? It turns out these 7 pieces have same statistical distribution. So their expectation should be the same. So the expectation of the first piece is 1 over 7, so which is this. So you can prove it, and it's actually, the distribution is actually, I think it's gamma. I forgot, I think it's beta or gamma, I really forgot. I think one of it. And you can actually get the variance. You can not only can get the expectation, you can get the variance bound. So you can do it. And then you use this. Then you can estimate F0 using master moments because you treat it as the correct value, and you get it from the master moments. And then, of course, if you only have one register, you're not going to be correct. I mean, very accurate on the answer, right? Because the smallest hash value can be very volatile. I mean, it can fluctuate quite a bit. But you know how to do it, right? You use say 100 independent hash functions, and then you get 100 such estimates, and then you do some kind of average. I mean, it's easy to say you average it up, but you average hundreds of such estimation up to get the accurate result. But in reality, if you have statisticians here, I mean, those people will say that typically median estimate is better than mean estimators. So I think indeed, if you use median estimate, you can get very good estimation. And now I think I'm ready. I feel ready to talk about this is my second data streaming work. I mean, this work is for estimating flow size distribution. And I'm actually quite lucky because this is my first ACM sigmatrix paper, and it turns out this paper gets the best in paper award. So it gives me a lot of encouragement for continuing doing data streaming work. So the problem is to estimate the probability distribution flow sizes. In other words, for each positive integer I, you estimate ni, the number of flows of size I. So you want to know how many flows of size 1, how many flows of size 2, how many flows of size 3. It has lots of applications in traffic categorization, engineering, in the network building, accounting, and anomaly detection. So I just want to give you one example. In old days, I think the worms, all the internet, a particular type of internet worm has a fixed size, for example, like 1,000, say 1,300 bytes. And typically, I think you only have like a couple of variants of operating system. For example, there's Windows, there's Unix, and typically you cut an object into packets of size like 500 bytes or I think Unix is like a 512, or I think the Windows is like a 536. I forgot. It could be the other way around. So if you do this kind of division, you can see if you have an object of 1,300 bytes, then you will be split into 3 packets, right? This object is split into 3 packets. So if you see lots of worm propagation, then you will see lots of flows of size 3, right? So if you continuously monitor such flow size distribution and you suddenly see a particular flow size just shoot up, then you may suspect there's some kind of worm propagation or virus. So it can be quite useful in this kind of anomaly detection purposes. And it's also very important from an intellectual point of view because it's mother of many other flow statistics, such as average flow size and flow entropy. Because once you know distribution and everything else, you know the first moment, second moment, entropy, etc. So I think many of you may not be networking people, but you don't know. Actually, but the good thing is you do not need to know anything about networking to understand my talk. So because I think to a certain extent I think a lot of my work is sort of to a certain extent like marginal in the networking area. So basically, you can think about the definition of flow is like all packets with same flow label. And the flow label, I mean, for networking people, I mean, the flow label is basically source IP address, destination port, destination IP address, and the destination port and protocol. I mean, typically it's this, but there could be a subset of it. But for you who do not know much about networking, you can just think about it as a data label. It's just a label. So all the data with the same label belong to the same flow. It just means that. It's just a label. So architecture of our solution is something we call lossy data structure. We maintain, the idea is very simple. We maintain an array of counters. It's an array of counters in fast memory. And for each packet, a counter is chosen through hashing and incremented. And we do not detect or resolve collisions. And then, of course, these counters has to be long enough. For example, it could be as long as 64 bit. But we have some kind of scheme which can implement, we can implement a 64-bit counter using only 4 bits of SRAM. I'm going to show you how to do it. And so data collection is very lossy but very fast. I'm going to show you the animation so you know how it works. So this is an array of counters. Okay, counters starts with 0, and if you increment it, you increment by 1. So this is a processor, and then a packet comes in. This packet belongs to the red flow, and then you hash its flow label. You get the uniform distribution across this address range, and then it goes here. So you increment by 1. You increment this counter value by 1, so 0 becomes 1. A second packet arrives, it belongs to a different flow. It belongs to green flow, so it goes to a different location, increment by 1. And the red one comes, and it has the same label. So same label hashed to the same index, so it goes to the same location again. It becomes 2. Now there's a packet belongs to the yellow flow, and it comes in, and you hash it. Unfortunately, there's a hash collision. It goes to the same index because you could have lots of flows, and you will have a collision. So, but from God's eye, you know it's a collision between 2 red packets and 1 yellow packet. But without that view, you only see that this value is 3. So you only see these numbers. There's no way you can tell if it's a collision between 2. between 2 packets flow and 1 packet flow, or it's just a flow of size 3. There's no way you can tell it. And then some of you might say that, okay, suppose you have a large enough counter array and you assume there's very little like a collision, then you just look at these numbers and you treat it as a flow size distribution, that just works, right? But it actually does not work. I'm going to show you that, for example, with AT&T data. This is with AT&T data. You have about 1 million flows in it, and you can think about you map. So we have several curves here. It means you map this about 1 million flows into like 1 million counters, 500,000 counters, 250,000 counters, and 1/8 of a million counters. And this is the raw counter value distribution you get. So this is the correct. This is accurate. This is the actual flow size distribution, but this is the flow size distribution when you map. This is a raw counter value distribution when you map to 1 million flows. When you map to 1 million, this is mapped to 500,000, mapped to 250,000, mapped to 1/8 of a million. You can see it's quite different. Even the best one, you map to 1 million flows, the accuracy. So this is basically the flow size. This is not your estimation of number of flows with this flow size. You can see that, for example, if you want to estimate the flows of size 1, if you map to 1 million counters and you treat the raw counter values as a flow size distribution, then your estimation of flows of size 1 is very different from the actual number of flow size 1. Although they look close, but it's a log scale, so you're talking about 2 or 3 times difference. But sometimes the worm and the virus are very small, so they often show up as flows of size 1. So if you have the wrong estimation, you might think everything's okay, although there's a massive amount of like a worm or virus going on. And we can do much better. I'm going to show you how to do much better. And so we want to be able. So basically, using raw counter values does not work. So we have to use some kind of statistical methods to infer the flow size distribution from looking at these raw counter values. So that's basically our estimation part. And by looking at these raw counter values, you can immediately infer certain quantities. For example, you can estimate the total number of flow n and the number of flows for size 1, like n1. So let us see how to do it. So let the total number of counters be m. You know this quantity, right? Because that's the set quantity. And then let the number of value 0 counters be m0. Of course, you know it, right? Because after you run it, you count how many counters have value 0. And then you can prove that you have a very nice estimator, n hat, which is m times log m divided by m0. This is m, this is m0. So which means this n hat is a pretty good estimator for the total number of flows. I think this is a done deal. I think it has been done like more than a decade ago. And I think people actually prove it's not only unbiased but also MLE. It's a perfect estimator. And then you let the number of value 1 counters be y1. You know it, right? Because you look at these counters, you just count how many of them have value 1. And then we come up with a good estimate of number of flow size 1, which is n1 hat equal to y1 times this, n hat over m. N hat is this estimator value. And yes, we can generalize this process to get number of flows of size 2, number of flows of size 3. But this is not going to work very well. Why? Because you can see that to estimate the number of flows of size 1, this estimator has n hat inside it. So and you can imagine that to get the estimate for n2 hat, you have n1 hat and n hat in it. To get and you can think about the error will accumulate if you want to estimate like n10 hat. It will have n9 hat and 8 hat in it. So generally, this process is not going to work. So the solution is we have to do some kind of joint estimation of all these quantities using some statistical methods, which is the expectation maximization. I'm sorry. So the EM algorithm works as follows. You begin with a guess of the flow size distribution. And based on this guess, you compute the various possible ways of splitting a particular counter value and the respective probability of such events. And then once you split this way, you will get a new distribution. And then you repeat this process multiple times, and they will converge to a local minima. It does not guarantee, EML algorithm does not guarantee to converge to the maximum likelihood estimator, but it will converge a local maxima, which is good enough in most instances. So I'm going to show you how it works out. For example, a counter value of 3 could be caused by 3 events. 3 equal to 3 means there's no hash collision. It's a flow of size 3 when you see a counter of value 3. 3 equal to 1 plus 2 means a flow of size 1 colliding with a flow of size 2. It just means that. And it could mean 1 plus 1 plus 1. And suppose the respective probabilities of these 3 events are 0.5, 0.3, and 0.2 respectively. And there are 1,000 counters with value 3. Then we say that whenever we estimate that 500, 300, 200 of them split in these 3 ways, because it's 1,000 multiply these 3 quantities. Some of you may wonder, how do you get these probabilities? And these probabilities actually can be obtained by having this initial guess. Once you have this initial guess, conditioned, based on this initial guess defines distribution. Based on distribution, you can actually get these probabilities. These are like Bayesian methods. So once you have this you treat this as a priori distribution, then you will get, and these are computed as a posteriori distribution. You can actually get it. And then you estimate these 500, 300, 200 counters split in these 3 ways, and then you actually split it, which means you actually cut up these counters and you get these dusts, and then you just put the dust into the right place. Guess what? Once you put all the dust into the right place, you get a new distribution, and then they use this new distribution to compute these probabilities again. And once we have done it, the result is remarkable. So I think this solid curve is the actual flow side distribution. You have seen these 2 curves before, right? Because this is actual flow side distribution. This is when you map to 1 million counters. You map something like 1 million flows to 1 million counters, you get this raw counter value distribution. But we should have 3 curves here. The 3rd curve is the estimation in our algorithm, but we only have 2 curves. The reason we can only see 2 curves is our estimation coincides with this actual one very well. But there's a little bit, you can see it's actually 2 curves because you see a little bit glitch here and there. But it's pretty close. It's steep. Did you see these ones, right? So it's actually 3 curves. So there's some difference down there. So the result is very good. So I want to skip some comparison with the sampling. I think and proceed to the next one. So this is basically so we just talk about the estimator. How to estimate flow side distribution in the data streaming algorithm. And remember, this data streaming algorithm require an array of counters, right? And we actually do require the number of counters. The number of counters we use, it has to be on the same order as number of flows. So you could have like 1 million flows, like 10 million flows. So you need lots of counters. But remember, some of these counters actually counts the number of packets, right, which map to it. And this count can be pretty large. It could be even more than 4 billion. So you need not 32 bits, but 64 bits in it. So you need a large number of counters, which are pretty long. Okay, a large number of long counters. But it's very expensive to put. I think these counters has to be in SRAM. So if you have a large number of long counters, it's very expensive. So we want to reduce this cost, and this is our scheme to reduce it. So we have a hardware primitive for counter management, which I think reduces cost significantly. So the problem statement is to maintain a large array of counters that needs to be incremented in arbitrary fashion. So which means you control an array A, and the customers specify this index to be incremented. So the customers give you I1, I2, I3, these index, and you have to increment these index by 1. So increments may happen at a very high speed. So you have to use high-speed memory, but the values of some counter can be very large, just like in the flow side. You see in the flow side distribution work. But fitting everything in an array of long SRAM counters can be very expensive. If you have like 10 million counters, if every counter is like 8 bytes, that's 8 megabytes. It's very expensive. And many of you think about the caching, but let's assume there's really no locality in index sequence. So I think you can think about it's controlled by the adversary, right? It's controlled by adversary, so there may not be locality. So if you want to use caching to reduce the number, the memory size, it may not work. So it has lots of motivations. I think I already motivated from the data streaming point of view, but there's also other motivations, like router may keep track of many different counts for different kind of source message IP prefix pair, and to implement millions of token leaky buckets on router. It's actually, I think the funny thing I always talk about is extensible to other non-CS applications, sewage management. I'm going to revisit this once I think we are close to. So our work is able to make 16 SRAM bits out of one SRAM bit that I call the alchemy of 21st century. So let's see how to do it. The main idea so there has been some approach, I think, by other researchers. So so this architecture is not my original idea. So there's a general architecture to reduce the amount of SRAM you use by using some kind of hybrid SRAM DRAM architecture. So the way it works is, you can think about, you need to maintain 1 million counters of size 64. Instead of maintain 1 million long counters in SRAM, you only maintain 1 million very short counters in SRAM. And then, but then you maintain these long counters in DRAM. And then the increments goes to these small counters first. Small but fast counters first. But once it becomes like half full or almost full, you do some kind of flushing. But it turns out this, for example, if the counter 1 becomes almost full, you flush to this counter 1, things like that. And then it turns out the trick is to design a good counter management algorithm. It's very hard to design because you have to think about adversarial condition. I mean, you can say there's adversary try to, your algorithm has to be known to the adversary, and the adversary can change, I mean, the access order or something to derail your algorithm. So there has been 2 previous approaches. I think they don't work very well. I think I want to skip it. I just go directly to my algorithm. So they don't work quite well. I think I'm going to email you the slides so that you can share with colleagues. So I'm not hiding anything down there. So our scheme, and you will know that I think it's justifiable for me to skip the previous 2 slides once I tell you my solution. So our scheme only needs 4 SRAM bits when the speed difference between SRAM and DRAM is 12. So I'm getting about 60 nanosecond DRAM, 5 nanosecond SRAM. So just assume the speed difference 12. And then think about that. If the speed difference is 12, then you need at least 4 bits, right? Because if you only have 3 bits, then every 8 cycles you flush, right? But DRAM is 12 times slower. So it's not going to work out. So you need at least 4 bits so that you can think about the DRAM load factors like 12 over 16, which is 75%. Right? You need at least 4 bits. And yes, we can just use 4 bits. So it's kind of optimal. So our idea, you flush when the SRAM count is completely full. So which means if it goes from 15 to 16, it's completely full, right? Then you flush it. And then we use a small amount of SRAM FIFO buffer to hold the indices counters to be flushed to DRAM. So which means, for example, if the index 137 goes from 15 to 16 because of increment, then we just put 137. We just append 137, which is the index, into this FIFO buffer. And then eventually, this DRAM block index 137 will be incremented by 16, right? You flush. Of course, when you flush to 0, right? You flush to 0 for the SRAM thing to flush to 0. So our key innovation. So this is a simple algorithm. Our key innovation is a simple randomized algorithm to ensure that the counters do not overflow in a burst large enough to overflow FIFO buffer with overwhelming probability. So that's our main innovation, and our scheme is provably space optimal, of course. So here's a randomized algorithm. We set the initial values of the SRAM counters to independent random variables uniformly distributed in 0 and 15. So you have 1 million counters. For each and every of them, you set them to a uniform random number in this range. but counters has to count from 0. So you have to remember this initial value, and you remember it as a negative in the DRAM. So you set the initial value of corresponding DRAM counter to negative the SRAM counter value. And then adversaries know our randomization scheme, but not the initial values of SRAM counters. And this adversary defined in the well-defined notion of something they call online algorithm. So, and we prove rigorously that a small FIFO Q can ensure that the Q's overflow with very, very small probability. So I mean, going to the sewage management. So that basically, you can think about there's 1 million homes, say in not 1 million, say 10,000 homes in a subdivision, and then you share a sewage tank of like 300 toilets or something, and then of course your pumping station has to be fast enough, right? If the pumping station enough, I mean, you can think about the load you pose on the pumping station is like 75% or something, okay? And but you need some kind of ordinance in the subdivision to make sure the sewage tank does not overflow. And your ordinance is basically you cannot flush. Ordinance number 1, you cannot flush until your toilet is completely full. That's ordinance number 1. Ordinance number 2, when the new homeowner moves in, he has to set the water level to a uniform random level between 0 and the completely full. So with these two ordinances, I can ensure that this small sewage tank in subdivision will not overflow for 1 million years or something. So this is a numerical example, and you have 1 million 4-bit SRAM counters and the 64-bit DRAM counters with speed difference of 12, and suppose you have 300 slots in the FIFO Q for holding indices to be flushed, and after like a trillion counter increments, you can think about like monitoring 8 hours of network traffic on like a 40 gigabits per second link. And the probability of overflowing from the FIFO Q is something like a 10 raised to the power minus 14, which is about mean time between failures like 100 billion years. And it's actually longer than from Big Bang to now. So, and then we prove, it's actually to prove guarantees like this very hard. And we use a lot of minimax analysis and large deviation theory, which I'm not going to talk about here. So I think I still have another set of slides, which is even more exciting. But I think to conclude this set, I think data streaming is a very powerful tool for network measurement and monitoring. And there are challenging research problems arise due to stringent space and speed requirements. And distributed data streaming is even more exciting. And the challenge, which I'm going to talk about in the next set of slides, I promise to be very fast on that. Yeah, sorry I did not merge it because this set of slides is done by my former student, now postdoc, who use a very esoteric set of latex tools, which I'm not able to merge. So it's actually called data streaming algorithm for estimating entropy of OD flows, and with these are two of my students, and then my collaborators at Rochester and the AT&T. And let me show you. So these are called the origin destination pairs. So you can think about these are these are all access points. These are like ingress access points of a network. These are egress access points of network. You have lots of flows between ingress point and egress point. It's actually, I mean, at AT&T, for example, you have 100 ingress points, 100 egress points. You're looking at the 100 by 100 traffic matrix. And the problem we're looking at is there's given a particular flow. I mean, flow means the OD flow, origin destination flow, means all the traffic which goes from one particular ingress point to one particular egress point. And there's lots of traffic. Inside it, you have lots of TCP flows. I mean, let's call it micro flows. And we want to know the entropy of these micro flows. So by the way, I did do some entropy work, but the work is I did some other entropy work, but the work is on estimated entropy of what we call the total population, which means you can think about all the traffic within a link, we can estimate its entropy. But this is basically entropy of a subpopulation, right? Because there's the total traffic is going from all the ingress points to all the egress point. But this is just a subpopulation. It's actually a very particular subpopulation, which means it's actually, you can think about it as this set. If you think about these packets as a set, this set is the intersection of all the packets that going out from this node with all the packets that going to this node, right? It's a set intersection. So it turns out by like 2006, there has already been like 10 papers on entropy estimation, but no entropy estimation work has been able to handle the intersection. So you can estimate, there are 10 different algorithms for estimating the entropy of a set, of a data stream, but but none of them is able to solve the problem of estimating the entropy of the intersection of two data streams. But union intersection can be very powerful and very useful in many situations. So I think I'll just quickly go through the definition of entropy. So this is the definition of entropy. The PI is the fraction of traffic from the ith flow. And turns out, so we want to know, for example, if you have suppose we have 6 packets and they belong to 3 different flows. Suppose there are 3 packets belong to one flow, 2 packets belong to another flow, and 1 packet belong to yet another flow. Then its entropy value is 3 over minus, and everything take a minus sign. So 3 over 6 log 3 over 6 plus 2 over 6 log 2 over 6, 2 over 6 plus 1 over 6 log 1 over 6. That's entropy value, okay? And it turns out to estimate this entropy value, it's equivalent to estimate the what we call entropy norm. So entropy norm just is this pi is just mi, which is number of packets inside the flow I divided by total number of packets m. So you can see these two things are quite equivalent. And there's lots of motivation for entropy because many other people has used entropy for a lot of different things like anomaly detection, traffic clustering, and things. So there's a need to estimate the entropy value. Although but in all these papers, all these papers, the estimation is offline. So if it's offline, then you can just use the precise notion of entropy on it. You don't need any data streaming algorithm. But we want to do it in online setting. It turns out that very magically, we are able to connect entropy with something very fancy in statistics called stable distribution. A distribution D is called the p-stable, and for any constants like a1 to an, the random variable x1 to xn drawn id from this p-stable distribution, this linear combination of these random variables have same distribution as this random variable multiplied by the LP norm of these parameters. So this is a stable distribution. The example stable distribution is like Gaussian distribution is too stable, right? Gaussian because ax plus by is equal to like square root of x squared plus b squared z. Right? They're equivalent. So I think Gaussian is like too stable, and if you know Cauchy is one stable. So stable distribution has, I think, that several types of stable distributions are very well known. So stable distribution actually exists for p between 0 and 2. So 2 is like Gaussian, and 1 is Cauchy, but there's a whole range of them. And the closed forms are known only for p equal to 0.51 and 2. Although closed form is only known for these 3 values, but there are known formulas for generating samples from all the stable distributions. So this is something they call the Chambers formula. There's been work by MIT professor Indyk. I think his conference paper is actually year 2000. So you can estimate the piece frequency moment of the stream. You can estimate the LP norm of data stream using this stable distribution. Using this algorithm. I'm not going to go through this algorithm actually. It turns out this work comes out of a critical insight. The critical insight is that you can approximate. It turns out you can approximate a function x log x using a linear combination of 2 power law terms. So which means you can approximate this function by x raised to the power 1 plus alpha minus x raised to the power 1 minus alpha multiplied by this c. You can actually do that. And for example, I can show you the quality of approximation. I think this constant is wrong. It's actually we approximate x log x by x raised to power 1.05 minus x raised to power 0.95, not divided by 2, but multiplied by 10. So this function can approximate x logs very well. You can see that this is the solid line is approximation, and the dashed line is x log x. So this approximates very well. And then, but of course, there's a range of approximation. So for example, within 1,000, you can do very well. Actually, even within 5,000, your approximation is pretty good. And then, once you can do that, then everything adds up, because you can see, suppose this is the flow 1. Flow 1 has m1 packets. So this quantity m1 log m1 can be approximated by c times m1 1 plus alpha minus m1 raised to power 1 minus alpha. And then for every flow, you can do that. You add up the left side, you get entropy norm, which is equivalent to entropy. You can show that once you have entropy norm, you can get entropy, and the other way around. And then when you add up the right-hand side, you'll see that you have a 1 plus alpha moment, you have 1 minus alpha moment, which can be estimated using stable distribution. And the good thing is the stable distribution work extends to the intersection union. You can do intersection union using stable distribution. Although the original author of the stable distribution work did not state it, but we extend that work to the intersection union. So once you can do intersection union of this quantity, you can do the intersection union of this quantity. So this is basically the way intersection union works out. So you have some kind of sketch, some kind of data structure called a sketch at the input point, in the ingress point. You have the sketch at the egress point. It turns out you can do some kind of linear operations on the sketch. This means term-wise subtraction, term-wise addition. And then, and think about it, this is the intersection, right? So you can think about at the origin side, you have these flows. At the destination side, you have these flows. You can see these are the intersection, right? It turns out if you do a term-wise subtraction and then you estimate from it, you get these two terms. And then if you do a term-wise addition, you basically add things up. You get these two terms plus a scaled form of this term, and then you can come up with two different estimators because we want to know this term, right? We want to know something regarding this term. It turns out you have two estimators for it. One is takes the difference between these two and scale by 2 raised to power p. And the other is just O plus D minus this. I think, as far as I remember, this thing works better because for this one, both needs estimation. So you have two times estimation error or something. And then I think let me skip this, and we do some kind of data collection AT&T, and this actually works pretty well. So I think I'm not going to get into detail because I want to talk about something else. So this is how it works. Basically, you approximate this function x log x by 2 power law terms, and then we aggregate on both sides. On the left side, you get the entropy norm. On the right side, you get the LP norms. And it turns out the entropy norm can be approximated by the combination of two LP norms. And the LP norms can be estimated using existing data streaming algorithm. So, and it turns out this work has generated quite some impact because there's a MIT work, which I think it's in Stock 2008. Our work is in a system conference in 2007, but there's Stock 2008, which is about how to use approximation theory to do data streaming. So which means you approximate a function using some polynomial, like a Bernstein polynomial or something. There are lots of approximation polynomials, and they are able to they developed some kind of approximation theory for data streaming, and it turns out this is the first work on using approximation theory for data streaming. And also it also has I was also able to connect to the work of statistics people, because recently there is a Cornell statistics professor who developed some technique on accurately estimating. So remember, you have to get this LP norm from this stable distribution, right? And the typical estimator for doing that is the median estimator. So the median estimator has been used for many years. It turns out that recently the Cornell researcher found out that for stable distribution random variables, if the stable parameter p, if the stable parameter p is around 1, I mean, in my case, it's 1.05 or 0.95, which is very close to 1, then the harmonic mean estimator is like 1 order magnitude better than the median estimator, which is significant for me because previously I need to collect suppose I need to collect 100 samples to get this epsilon. Now I only need to collect 10 samples to get epsilon, which means the number of memory writes is reduced by 10 times. So that's the reason recently I work very close with, our team worked very close with him to actually implement this estimator to see if it helps us like on 1 order magnitude, which saves us like 10 times memory bandwidth, which is very, very significant. So I want to stop here maybe to answer some questions. Yes?
The first part of the talk, you started by saying that sampling wasn't a good idea, and I didn't quite follow the book example, but do you have some empirical results that show how sampling actually compares when you're trying to find load or?
Yeah, I think that's the slide I skipped. I think in the previous talk. Let me see. I think in the previous set of slides. I think. So I think this is basically flow side distribution. This is our estimation results, and which coincides pretty well with the actual flow side distribution. But these are the estimation from sampling. So that's by Nick Field, by the Nick Field, Karsten Lund, and Nicole Thorup at AT&T. So they show that this is I think when you sample with 1%, you get this. You try to recover it, you get this curve. When you sample with 10%, you try to recover, you get this curve. You can see that there is some kind of gap. I mean, it's because, for example, if you sample with 1%, then it's very hard for you to recover the number of flows with size, say, 101, 102, 103, right? It's very hard because when you see a flow of size 1, you don't really know if it comes from a flow of size 103 or comes from a flow of size 1. You don't really know that. And it turns out the reason why they have a gap is they use EM algorithm. It turns out that their EM algorithm gives some negative values here. Of course, negative value doesn't make sense, so they have to truncate the negative values and make it 0 using the iterative proportional fitting. But this thing gets zeroed out. So I think there has been some work recently on comparing the power of sampling and the streaming. And how to actually, I did some work on how to combine the power of two schemes because they get different kind of spectrum data.
So that scheme is just picking at random 1 out of 100 or 10 out of 100.
Yes.
On a packet level.
Exactly. Yeah.
Okay.
There's also flow sampling, but flow sampling can be quite difficult for like hardware. From hardware point of view, it's pretty hard. And I actually have some work on how to do flow sampling, which is hardware friendly. So. Yes?
There's an article a couple of months ago in the IEEE Spectrum on using entropy to fingerprint for internet traffic like worms and things like that.
Mm-hmm.
And it has a lot of interesting curves, but unfortunately the people who develop the worms now monitor the flow, and then you don't have like the fixed site packets that you were mentioning.
Exactly, yes.
And they also are random when the worm injects itself into the system.
Mm-hmm.
See any changes applying your method to address those issues?
Yeah, I know it's well. I think it's interesting. So when I wrote these papers back in 2004 or 5, I can still claim worm as a motivation. So it's like now I no longer can claim that. So I think because worm gets more sophisticated, and just by looking because although I claim this as motivation, but just look, I mean, if you just look at it closely, what I get is a bunch of statistics, right? It may or may not be applicable for security applications. So that's the reason I always say that I think I'm very careful not to say that, not to claim this is security work, because I just say the security experts may find useful for such statistics, but because all these, just like you said, the virus worms gets more sophisticated, so you need more than just these summary statistics to analyze these virus and worms. Yes, so I can only, so the answer is I can only give you statistics, and whether they are useful for worm or virus detection, you may need some external domain knowledge on that.
Over there.
Yes.
Yeah. So you mentioned one reason why people would do sampling but would not inspect every packet in the router is the space constraint. The constraint is actually the processing constraint.
There's also CPU constraints as well. Yes.
Like in your case, your approach would actually inspect every packet. Do you have an idea whether that would affect the processing power, processing throughput of the router?
Yeah, CPU is usually pretty fast. I think it's the gigahertz CPU. Like, I mean, nowadays have 3 gigahertz, and every nanosecond you can process like 3 instructions. So with CPU, and I think now we have even something even better, multi-core, right? You could have like 16 CPUs, 16 like cores inside the CPU. So I think that kind of processing should not be a problem. I think I/O will still be the major bottleneck.
Am I missing something over here? The inference with sampling any constraint is almost matching the actual flow distribution.
No, actual flow distribution is no, it coincides with this one, because this is solid one. This actual one is the light dark, which actually coincides with this one, and you can see the traces of it. These are light dark curves, which goes actually with the red one, which goes with the red one. So this one is the dark black one, which is different.
Any more questions? Over there.
Yes.
I have one question. You mentioned that your algorithm depends on the probabilities
Mm-hmm.
for calculating.
Let me try to. Yeah, I think. So let me give you intuition. Basically, you first get a prior. Suppose you know the flow size distribution, right? Because remember, EML algorithm, you assume some flow size distribution to start with. Given this flow size distribution, you can actually compute. You can compute how many flows goes to a particular bucket. That's actually approximatable by the Poisson distribution. So I mean the hashing approximated the effect of hashing approximated as Poisson. I mean has been well established in the hashing literature. And then once these Poisson stuff collide, then you to analyze the collision effect of this Poisson distribution, you can use basically it's a Bayesian analysis, which means you can think about you see suppose a flow size 3, right? You have 3 different cases, and all these 3 cases have a prior distribution. Then you just distribute. You can think about just distribute your a posted distribution. You divide your a posted distribution proportionally by these a priori distributions. So this is sort of pretty well standard. It's pretty standard like a Bayesian statistics. And so it's basically the hashing analysis, the classical hashing analysis with Poisson approximation plus Bayesian formula.
Okay. Let's thank the speaker.
Yeah, thanks. Thanks.
Even I could follow.